ladies and gentlemen, this class recording has started. So, on Thursday, we went through the process of drawing this big, complex picture. First, what is this a picture of? Not an orbital, orbitals, right? So this is a picture that shows several different orbitals, right? The idea of an orbital basically comes from the work of two scientists that we've introduced before. Who are the two scientists that are most responsible for the idea that electrons exist in orbitals? Schrodinger is one. He's sort of the second guy. Heisenberg is the other scientist, all right? So, if you take a look on the first page of the outline, so flip that outline over to the front, all right? The title of this outline is called Location of Electrons in the Quantum Mechanical Model. But location is in quotation marks. Why is location in quotation marks?
They have no relative location.
Okay, they don't have, or at least our orbitals are not the exact location of these electrons. What do the orbitals represent? Possibilities, or maybe a better word would be probabilities, right? That orbitals represent areas where we are likely to find electrons. How do we know that these are areas where we're likely to find electrons? That's where they've been before, right? And so we make these drawings that show where electrons have been in the past, and we make a prediction that that's likely where they'll be in the future, right? So, first page of your outline, okay? I think you might have filled in a little bit of this stuff when we were watching, when you guys were watching the video on Wednesday of last week, because I filled in some of this stuff with the previous class, but, right? So uncertainty in Schrodinger's wave equation. The work of Heisenberg and Schrodinger led us to the conclusion that the exact location of an electron can never be known. We do have Schrodinger's wave equations. These wave equations, first, are really complex, but second, but second, they reveal areas of high electron density. Even though we don't know exact locations, we have areas of high probability, and we know that because they've been there in the past. So these areas of high probability we call orbitals. They're not orbits, right? They're not defined locations, but they are general areas. Okay? What's one way that orbits and orbitals are similar to one another? This is a quiz question. What do they have in common? How about if I say quantization? Does that help you at all? Okay. Good. Not necessarily, no. But the size is important that relates to something else about the electron. Nope, definitely not the mass. Let's go. The energy, right? How does the size of an orbit or an orbital relate to the energy of the electrons? Bigger orbitals or bigger orbits means what about the electron's energy? More. Farther away from the nucleus, orbits or orbitals that are farther away from the nucleus have electrons that have higher energy. Orbits or orbitals that are closer to the nucleus have electrons that have lower energy. Okay? All right, good there? Okay. So we have this big picture that shows all of these orbitals. And we went through the process, right, of going through building it up and all that good stuff, right? But each one of these is a separate orbital. So, because this is what we do in science, right, we look for similarities, we look for patterns, but we need to make sure that we represent that pattern or represent the similarities and differences between all of these orbitals. So today, we're going to focus on something that we call quantum numbers. And in quotation marks, it says the electron's address. what does your address tell me? Okay, where you live, but more importantly,
Where my house is located.
where your house is located. What does it not tell me? Where you are, right? Is your house a probable location for you? Yes. Is it exactly where you are though? No. Not necessarily, right? Excuse me. So, just like the address of your house, quantum numbers have, first, each orbital has a unique set of quantum numbers. Your house has a unique address that makes it different from every other house in Westlake, but every other house in the United States, right? It's a unique address to that location. Just like an address, it's not the exact location of an electron, it's a probable location. And we'll see, hopefully by the end of today, that there is a combination of 4 numbers that set that orbital apart from all the other orbitals that we drew in that picture. That we can describe every specific orbital in that picture with a set of 4 numbers that is different combination of 4 numbers than every other orbital in that picture. Okay? Good for starters. Okay. So the first quantum number that we're going to talk about today is the principal quantum number, right? So there's the title, right? Are we good with the difference between principal and principal? That there are two words that are principal, but they're spelled differently? Yes? Right? Yeah, right? So principal, P-R-I-N-C-I-P-L-E, is like an idea or a concept, okay? Heisenberg's uncertainty principle is an ideal, okay? But principal, P-A-L, means what? The main, the most important, right? The highest level, okay? Like our principal at school is P-A-L, right? He's the person that's in charge, okay? So this being the principal quantum number, P-A-L quantum number, that means it's pretty important, okay? So the first thing that it tells us, first, we use the lowercase letter n to represent the principal quantum number. And the principal quantum number is the main energy level where our electron is found. As we just discussed, if it's describing the main energy level, what tells us about the energy of the electrons? Generally speaking, or at least most importantly, what tells us about the energy, or what factor determines the energy that electrons have? How close they are to the nucleus, right? So the principal quantum number, if nothing else, describes how close this orbital is to the nucleus of the atom. Okay? So the principal quantum number, right? Orbitals closer to the nucleus have lower principal quantum numbers, and they have electrons that have lower energy. So at its core, the principal quantum number basically describes how far away from the nucleus this orbital is. Okay? If you want something that might be helpful, right? Yes, I have the outline there for you, and yes, there are things you can fill in, but little notes might be good, right? Nowhere up here does it say that it describes how close to the nucleus this object or the orbital is. Might be a good idea to jot it down in the margin, right? If that's something that might help you remember what these numbers, these quantum numbers are describing for you. Okay? All right, good for starters? Okay, so this picture over on the right is the last picture in the progression of our atomic models from the previous outline. Right? This is Schrodinger's model of the atom, right? It doesn't have it doesn't have defined shells. It has probable locations, right? But even when we look at these probable locations, as we move out from the middle, right? The middle's real dark, but then there's sort of a lighter green area, then there's another sort of dark band, then there's a lighter green area, then there's another dark band, right? Increasingly further away from the nucleus, we find areas where we're more likely to have electrons. But if we talk about these bands, right, what would we say about the electrons that sort of show up in this area right here compared to the electrons that show up in this area out here? The ones closer to the nucleus, less energy, right? The ones farther away from the nucleus, more energy. Okay? Good there? All right. If we take it back to our picture, okay? Let's see. Okay, so here's the progression. Yeah? Okay, this is what we drew. Okay, we started here. What is the black dot representing? Nucleus, right? So we got this, right? Then we got this. Then we got this. Right? And then we got this. Okay? What do you think might be representing the principal quantum number of these electrons, or of these orbitals, my bad? Any ideas? What might help us represent the principal quantum number? Critical thinking, everybody. Ian. Okay. You're on the right track, Ian. Okay? What happens every time a circle shows up? New color, right? But what did we say about each one of these new circles? What are they doing?
Layering.
They're layering, right? They're sort of encompassing all the other orbitals that show up. So on this drawing, every time we change a color, that's a new principal quantum number. Okay? So, if we go back to this orbital, the first one that we drew, how close is it to the nucleus? Really close, right? And so, if we're starting to describe this orbital and differentiate it from all the other orbitals, we're going to start with the principal quantum number. So, we said lowercase letter n represents the principal quantum number, and if this orbital is the closest one to the nucleus, what number do you think we're going to use to represent orbitals closest to the nucleus? 1. Okay? So, this orbital has a principal quantum number equal to 1. So, n equals 1. Right? This is where the colors are going to be helpful, right? Also, too, maybe you use different colors on different of the different small XY axis, XYZ axis down at the bottom. That might help us differentiate one from the other. Just some suggestions, okay? Okay, good with this? Okay. So, the next one that we drew looked like this, okay? First, there was a color change, and we got a little bit farther away from the nucleus. So, if we have to tell this one apart from the previous one, we're going to start with its principal quantum number. If this is the next one out, probably going to use number 2. Alright? So the principal quantum number for this orbital is equal to 2. This is n equals 1. This is n equals 2. Okay? Yes, Mo?
So
Let's talk about that right now. Okay? So, here's where the pattern gets a little bit more confusing. Okay? Because, so these are the hourglasses we drew, right? Okay? But, what are you seeing about the color of these hourglasses compared to the color of the circle? They're the same color, right? They're a little bit farther out from the nucleus, but they are the same color. And so we said that from a location standpoint, colors represent principal quantum numbers. That means, I'm going to go with this one first, that means that this orbital, even though its shape is a little different, a lot different, even though its shape is different, And it's a little bit farther out from the nucleus. This here also has a principal quantum number equal to 2. Okay? Remember, there's 4 numbers we can use, right? We can't assign a different number to every single orbital. It just gets too crazy. But there's a pattern in the numbering that tells us about the orbital specifically. So this also has a principal quantum number equal to 2. But guess what? This one also has a principal quantum number equal to 2. What did we say was different about this orbital versus this orbital? Different axis, right? This one runs along the x-axis, but this one runs along the y-axis. But they have the same principal quantum number. So go ahead. Good. Every time the color changes, there's a new principal quantum number. That means here, right? What's going to be the principal quantum number here? It's going to be 3. Okay. Lorenzo, go ahead. There are limits to the possibilities that they have. They're the same 4 numbers. Just like, so Lorenzo, every house on your street has like a house number and a street and a city and a state, right? And sometimes those numbers are the same. Like every house on your street has the same street name. And they're all in Westlake and they're all in Ohio. But there's something about the address that makes that address for your house different from all the other addresses. Okay? So even though we will see that some of these quantum numbers have similarities for different orbitals, there's always at least one thing that makes this specific orbital different from all the other ones. Okay? And that's what we're going to get. That's what we're building up to here. Okay? All right. Good with the idea of the principal quantum number. Okay. So if we take a look, right, we said that starting here, we have the first one, then we have a color change, right? Then we start adding new shapes, but the color stays the same. Then we add a new color. Then we start seeing a repeat of the shape, right? But then we added a new shape, right? We added like the butterfly or whatever we want to call this, right? And we said there were a couple of those. And then we went back to here, right? So even though we have different colors, we're seeing a repeating pattern in terms of the shape of the orbital, right? There's only a certain number of shapes or certain possibilities in terms of the shape of the orbital. So if we go back to your outline, I made a change as far as the order goes. So I want you actually to flip to page 2 of your outline and look for Roman numeral number 5. Okay? If I'm not mistaken. Yes, so Connor, that's a good question, right? So yeah, so Connor here, right? Connor asked, in this, going back to our drawing, right? Here, new color, this is the first green one that showed up, right? So that's when the principal quantum number shifts. So this one would have n equal to 4. And we could just keep going with that pattern indefinitely, right? The first time a new circle shows up, it would be a different color, and its principal quantum number would increase. Okay? All right. So on page 2, Roman numeral number 5, I believe, is labeled as the angular momentum quantum number. Is that correct? Okay. So the angular momentum quantum number, we use the lowercase letter L to represent the angular momentum quantum number. And I use a little script L to try and keep it different from number 1. All right. So you'll see I'll write it as kind of a recursive L. Okay. But as far as what is it telling us about it, it represents essentially the shape of the orbital. And we'll see that there are technically 4 shapes that we can have. And we call those shapes S orbitals, P orbitals, D orbitals, and F orbitals. And we'll explain those in just a second. starters. Okay. Here, again, we see an increase. This time we're starting at the number 0, right? The lowest value for L is 0, but then we go from 1, 2 to 3. So let's go back to patterns, okay? What kind of orbitals do you think are s orbitals based on our picture in the order that we drew things? Circles, but we said they're not actually circles, they're actually what? Spheres, right? Why? Well, every time we change the color, what was the first shape that we drew? Spheres, right? So s orbitals are essentially spherical orbitals. Regardless of what color they are in our picture, these are going to be our spherical orbitals, okay? And if you look at the little table right below, right? Oh, if you look at the little table that shows up right below this on your outline, right? You'll see that s orbitals, right? S orbitals are all spherical orbitals. And in comparison to the rest of the chart, how many spheres or how many options do we have as far as a sphere goes? Just one, right? Because how many circles or spheres did we draw in each new color? Just one. Okay? The next shape that shows up here on our chart is what? These are the hourglass shapes, right? Okay? Remember I told you that mine I kind of connected with a straight line and kind of put them on the side, but this is more what they look like, okay? How many hourglasses did we draw when we drew hourglasses? 3. Where were they? X-axis, Y-axis, Z-axis, okay? So, different shape, but we also see an increase in the number of possibilities, okay? Down at the bottom, what do those look like? What did I call them in class? Those are our butterflies, right? Those butterflies we refer to as d orbitals, okay? So, in this case here, right, I told you we drew 2 of them in class because I told you that we couldn't draw 5 of them because it just kind of gets really complex and it just makes your drawing a big mess. But how many d orbitals show up here in our chart? 5 possibilities for d orbitals, okay? And then the last set of orbitals we call f orbitals, okay? You can kind of see here in the chart it says 7 complex shapes. I'm not going to have you draw those. But, right, we see that as the shape changes, the number of possibilities increases as well, okay? Good for basics, okay? So let's apply this then to our picture. Okay? All right. Here's the first orbital we drew. We said its principal quantum number is 1 because it's the closest to the nucleus. But now we add a second quantum number. It's lowercase l, or script L. Script L represents the angular momentum quantum number. It describes the shape of the orbital. What shape is this orbital? It's spherical, okay? And we just learned that we call spherical orbitals what kind of orbitals? S orbitals. But in terms, so let me do it. This is an S orbital. Okay? In terms of the address, we call s orbitals, or we assign s orbitals a specific number, right? S orbitals, spherical orbitals, always get an angular momentum quantum number equal to 0. Okay? So here, this yellow orbital has a principal quantum number equal to 1 and an angular momentum quantum number equal to 0. All right? Good there? Okay. The next one we drew looked like this. So we said that it's a little farther out from the nucleus, and that increases the principal quantum number. However, what shape is this orbital? Spherical. That means it's what kind of an orbital? This is an s orbital. It's a little farther out and a little bigger than the other s orbital, but this is still an s orbital. Okay? And that means if we're going to assign quantum numbers to this orbital, right, its principal energy level is, or principal quantum number is 2, but it's still a spherical orbital, what do we assign as the angular momentum quantum number to all spherical orbitals? 0. Okay? So Lorenzo, kind of back to your question from before, right? These two orbitals are similar in that they're both s orbitals, but they're different because one's got farther out from the nucleus than the other one. You see how we're using the numbers to distinguish them, right? Like these both have the same L value, but they have a different N value, and now we got something different, okay? Good there? Okay, we're going to jump ahead, right? So here, the first blue one we drew was a circle, right? We said every time the color changes, that's a new principal quantum number. So we assigned a principal quantum number equal to 3, n equals 3 for this orbital. However, what kind of an orbital is it? It's a spherical orbital, and that means we call it what kind of an orbital? It's an s orbital, right? And that means that when we're going to assign angular momentum quantum numbers, what value does L get for this orbital? 0, because all spherical orbitals, regardless of where they are in relation to the nucleus, have L values equal to 0, because it describes the shape of the orbital. Okay? Good there? Okay. Now, let's go back here. Okay. So this was the first orbital that we drew that wasn't spherical. Okay? This is more of the hourglass shape. Okay? We said that because it's red, it still has the same principal quantum number as the previous one, but we have to describe it a little differently. Oh, wrong color. Angular momentum quantum numbers describe the shape of the orbital. Here, this is a different shape than the previous one we drew. Do we remember from the chart what we call the hourglass orbitals?
P.
These are p orbitals. Okay. Any hourglass-shaped orbital is a p orbital. So here, we have a p orbital in the second energy level. That means n is equal to 2, because its principal quantum number has increased by 1. It's a little farther out from the nucleus than the yellow one. But here, we assign a new value to L. If you look back in your notes, what value do we assign for p orbitals? 1. Okay? So, Lorenzo, going back to the question from before, right? These two orbitals, they're both red, right? But they have a different shape, so they have the same principal quantum number. N is equal to 2 for both of them, but L is different. Mo, go ahead. Okay, let me do the next one, and hopefully we'll, okay. So, sorry, Mo, if we're like, if you're like listing quantum numbers for an orbital, you can separate them by like commas or slashes or something like that, right? It's kind of like when you write your address, you know, it basically has 4 parts, right? It has your house number, it has your street, it has your city, it has your state, right? So we can make them a list like this, or we can separate them with commas or slashes or something, right? But it's 4 separate parts, 4 separate quantum numbers for each orbital, okay? All right, here. First, what shape is this orbital that we added next? It's an hourglass shape. And because it's an hourglass, what kind of an orbital is this? It's a p orbital. Any hourglass is a p orbital. Okay? And so, if we're assigning quantum numbers, especially angular momentum quantum numbers, what value does this get? 1. Okay? So if we look at the previous one, n equals 2, L equals 1, n equals 2, L equals 1, Now we're running into a situation where we have two different orbitals, but the same quantum numbers. That's where we finish this up, okay? So we'll pick it up from there tomorrow. We'll talk about the other two quantum numbers and how we use them to describe all the different orbitals. Good job today, everybody. I know, like, some of you, it's coming along, but I can tell we're making connections, all right? So keep up the good work.